Hi everyone, I'm Victor. Thanks for coming. I have the best slot in the schedule. Right after lunch, everyone is going to fall asleep now. I'm fairly confident. By the way, if some of you know what company I work for, or maybe if you enter the room hoping for some announcements or latest and greatest and that kind of thing. This is not that kind. I don't do those kinds of talks. Definitely the things I'm going to talk about today are not official company agenda. I don't represent the views of my employer. And some of them might not even know I'm here. And as always, I'm going to have opinions. So I'm going to present some facts, and I have data and links and references to prove them. And I'm going to compare some stuff, and I'm going to pepper that with some opinions and suggestions and questions for you. So by all means, I meant this as a dialogue, so feel free to interject at any point, ask questions, share your opinion, preferably if you can do it on the mic so everyone can hear and gets recorded, for better or worse. If you're reluctant to do that on record, I'll be here till the end of the conference. Just find me anywhere. I think you can easily spot me. And just corner me and say whatever you think about the topics. But I do encourage, I sort of, initially when I started working on this presentation, I jam-packed it with tons of information and lots of details, some of them technically interesting, but not really relevant to the bottom line of the idea. So in the end, I opted for more of a bird's eye view of things, and I've cut some of the ugly details, although I reference them, but I can chat about them offline maybe. Because I want to leave room for people to breathe, because I don't want this to be like a fire hose kind of presentation where I go through a lot of stuff and people are just overwhelmed or have difficulties following. And also I want to leave room for discussion and questions and interpretations. But first off, yesterday, during the morning keynote, I grabbed 2 bottles of water while Kevlin had technical difficulties with the projector. I grabbed 2 bottles of water out of the fridge here on the hallway. Can anyone notice what might be the connection between those water bottles and my topic? Do you have a good eye? Yeah. Shout it out.
Different interface, isn't it, at the top? So
yeah. Yeah. So, honest to God, I grabbed them from the same shelf in the fridge. And I even looked, so they're both still water. So I thought I grabbed 2 identical bottles. Not quite. So what does ABI really mean, anyway? Can mean a lot of things, and depending who you ask, depending on at what end of the food chain, so to speak, they spend their time, they might give you slightly different answers. If you're asking a compiler engineer or library writer or an application developer or a hardware operating system person, so they might give you slightly different answers. Is it the platform? Is this the hardware ABI? Are we talking about, I don't know, exotic architectures, calling conventions, language specification, compilers, how do we implement standard libraries, and how we share them, how we do dynamic loading, and so on. Then all sorts of things, they all sort of go under this ABI umbrella that everyone sort of talks about. So at the end of the day, it's about the, you know, when you say the devil is in the details, well, these are the details, the implementation things. And generally, we need to agree when we build stuff, we need to agree that stuff we're referring to means the same kind of things. And if we're building those caps for those bottles, they fit on bottles, even if they have like slight differences there at the top formation of the bottle. So we need stuff to just work. So ABI stability isn't really technically a property of the programming language itself, although people usually like to associate these discussions with language discussions and standardization. And it's really more of a property of a system or its tool chain. But because we strongly associate language names with their tool chains or their systems or their vendors or their platform that they support, we usually mix up these things. So some aspects are defined by the platform and the operating system, some by the tool chain, how the vendor chooses to implement things, or to support already shipped things. And there are many situations when the platform owner actually requires you to build with a particular version of the tool chain so that it works on the target operating system version. Apple would be a prominent example in this camp. Of course, this is a really big deal if you care about dynamic linking and about sharing libraries. And even here, we have a very wide spectrum of priorities and necessities, depending on the kinds of things that we're building. For many application domains, dynamic linking just doesn't make sense, isn't applicable, or isn't a priority. Whereas for other situations, sharing runtimes, sharing library implementations, thinking about code size and how you fit in the system, or how you can service those components while they're shipped. The ability, for example, to independently patch security vulnerabilities in libraries that are shared across multiple applications. The ability to service operating system fundamentals without requiring applications to recompile or retarget against those patched versions of the runtimes. So those are different concerns. So again, we have a very wide spectrum of what applications need and usually prioritize what we care about. So trying to be more concrete here. So layout of types, that's the first thing that comes to mind when you think about ABI. Size, alignment, stride. In some situations, this makes a difference when we talk about cohabitant of types. If you think about fancier constructs like enums that have associated types, and stride becomes important when you think about arrays. So size, alignment, offsets, the types of fields and their offsets in composite aggregate data structures, vtable entries if we have any such things in our types, calling conventions, name mangling, metadata if applicable for the language or the runtime in question. And yeah, name mangling matters because we're actually using 70s era technology for linkers. So just to build like a common understanding of what we're talking here, we have a source file that implements a particular definition for whatever types excuse me, we're defining there. And we compile this together in a unit. And on some other side, someone wants to consume some of this implementation, and of course, it will compile the source code against the definitions that we provide, and hopefully these things should somehow connect together. And I carefully placed those gears in the slide so that they look like they fit and don't grind together. So yeah. Binary compatibility between separately compiled artifacts. This is what the kind of thing we're talking about. And it's not just about evolving and modifying the type layout for a particular type. It's also about flexibility to upgrade or change your tool chain. For example, you might have these separate artifacts compiled with different versions of your tool chain. Or, dare I say it, maybe different tool chains, and you're sort of trying to mix them together. So we have to carefully orchestrate these kinds of things so that they just work, and we don't have any surprises. And the surprises can be really weird. It's not like we get nice diagnostics for these kinds of things, or we can easily uncover them. Sometimes they're really sneaky. They can seem to work and then mysteriously fail for some reasons when you least expect it, as usual. Okay, so the idea is we sort of want this predictability, this stability, so that we can freely mix and match, so that we don't have to share source code for a library, for example, so that we can access the most recent version of our compiler, our toolchain, be able to upgrade without worry that things might break, or I have some third-party dependency that I'm going to have to leave behind, or recompile, or I don't know, maybe the vendor went out of business and I cannot get a newer version of that DLL or whatever. So upgrading with ease. Don't recompile the world. Maybe even like a efficiency step in terms of build pipeline, like being able to just move forward without recompiling the world every time. The ability to incrementally do stuff. And yeah, I mentioned this earlier, the ability to actually patch stuff and address vulnerabilities in shared libraries, vulnerabilities in operating system foundational components without requiring applications to deal with that burden. And size does matter, yeah. When you're sharing a lot of, even for the standard library or some runtime that you're consuming, or depending on having that payload in every component that actually relies on it statically, it's a cost that not all environments can afford. So being able to share that code, again, it's a win. So the idea is that if you do want to have this stabilization and all these properties, when should you look for them? When should you opt in? If you do this too early, you end up shutting a door on future compiler or library optimizations, miss out opportunities, like, I don't know, implement a better calling convention, or change the layout of a particular data structure so that it's more optimal, or improve some detailed implementation of standard library facility, standard thread. And mind you, these are not impossible things. They're just tough problems. So it's not one of these 6 impossible things that Kevlin mentioned yesterday. These constitute lots of small little details that can be addressed with enough effort and desire to do so. Because I will question that not everyone actually cares about these things. So yeah, we need to invest a lot of time and solve them. But there are potential solutions. So I mentioned this earlier, ABI stability is not necessarily a language thing. It's, I would say, mostly a library evolution concern, and how we choose to improve, evolve the libraries that we're building or consuming. Developers want to evolve their libraries without breaking ABI, because then they'll have a better chance of their changes being adopted quicker. They want to add new functionality, fix bugs, improve performance problems. These kinds of activities can in some situations, generate ABI breaks and hurt consumers. For example, adding a field to a class, virtual function, we use some padding or some reserved fields and so on, could have surprising effects sometimes. And we've seen, for many years, we've seen implementations hold back on different improvement opportunities because they're just afraid they might break their client code. So if you're looking like let's say over the fence, whenever you don't know what to do, you look over the fence to see well, what do other people do. Well, I would say a bunch of our usual suspects there, they outright claim that this is not an active concern. They have different priorities. Well, C++ were always undecided, but I'll get into that. So for Carbon, for example, they state we have the explicit non-goals for Carbon, including a stable application binary interface for the entire language and library, and perfect backwards compatibility. So they just don't want to deal with this now. They have other priorities when building this emergent new technology. Rust should be more mature by now. They have plenty of facilities, maturity, tools, language means to deal with additions and fairly good tooling. Still, this is, by the way, this is comment is from 2015, but there's no news since. So Rust does not care about defining an ABI. So they're very much embracing the build everything, leave at head, sure, semantic versioning for crates, but build everything from source. So they have no such priorities, at least for now. Zig natively supports the C ABI for external things. Well, everyone tries to do that. But Zig internally does not use an ABI, meaning code should explicitly conform to C ABI, and all other assumptions are off the table. So again, no guarantees. Their focus is completely in other directions. Go, pretty much the same thing. By the way, they're not properly marked on the slides, but these are quotes from the pages. These are not my interpretations. So Go's ABI defines the layout of data in memory and conventions, calling conventions. This ABI is unstable and will change between Go versions. Like they flat out said it. No guarantees offered. So I mentioned this earlier. When dealing with these kinds of things, you have various considerations, various constraints, business priorities, technical limitations, user demands, and so on. So you have multiple choices, multiple things that you need to consider and prioritize accordingly, like what you want versus what you need or can deliver now to customers. So when we think about layout and stability of type layout, this would be the gold standard for stability, right? The one level of indirection solves every problem. Nicely fill in the room. I have to acknowledge level of indirection in the room. So yeah, you can indirect everything through a pimple-like interface, but that's it's not a scalable solution. It's not nice, and it does come with performance costs, even if you don't really need it. So it's sometimes employed, but it's not a pretty solution. Just erasing every trace of type rigor and performance, that's another choice. We can do that. I just heard Annie mention this morning. And of course, we have the greatest champion of ABI stability and dynamic linking out there. And by the way, that C is not carbon. It's the old C. The new carbon doesn't have a logo yet. OK, so when unsure, always go to the roots. I started programming in the 90s. I lived through a lot of COM. Do we have COM survivors here in the room? Yeah, OK, cool. About a quarter of the room. I'm impressed. So we all remember the COM way, where you actually want to change something, you just have to invent a new interface. So you force breakage through API, and you force your users to use extended interfaces. For example, if you want to add one more function to your interface, you cannot just add one more function. You invent a new interface. And by the way, that 2, 3 suffix there, that's not slideware. This is the naming convention that we used for the folks who are not aware of those historical tidbits. So yeah, I have vivid memories of using interfaces that had a 5 or a 6 at the end. And they were not mine. That was Windows provided stuff, good stuff. Or you can take the stringly approach of things like Objective-C and go for more of an unstructured data, type erasure, galore, dynamic everything, in directions everywhere. So that works, but comes with other disadvantages in optimization opportunities, in type safety, in refactoring capabilities, and so on. So specific stuff when you lose type information. So, and now I'm getting to the uglier bits. By the way, you haven't thrown things at me yet, but I'm still available. So in February 2020, the last pre-pandemic ISO committee meeting that took place in Prague, there was, I was about to say productive, but it wasn't productive, but it was the most vivid discussion on ABI stability for C++. And they took a series of polls, and we decided not to break ABI. Sort of, that not is weird, because we also don't offer any guarantees.
That's not right.
Sorry?
That's not right.
What do you mean?
We decided not to break for C++ 23.
Yeah, I have a slide with those concrete things. I think it's the next one. Oh no, the next one is ugly. But it's coming up. Yeah. Like Daniela interjected, I would say the outcome wasn't a definitive answer. Like all things C++, it was ambiguous. So soon after that committee meeting, Corentin wrote this article, the standard library died. And by the way, highly recommended. If you haven't read it yet, highly recommended that you read it. It's not as gloom as it looks in the picture. So I had to put this up because I so very much love that quote from Titus. So committing to ABI is like admitting that the standard library is aiming to be the McDonald's. It's everywhere, it's consistent, and it technically solves the problem. But I think we could agree that's not really good food. So that's one of the issues. How far do we extend this discussion? And not including the standard library in the ABI discussion is just like, why are we talking about it? If we're settling for a subpar standard library just because it's everywhere and makes these stability guarantees without being any good, and we have plenty of examples, then why are we talking about it? Maybe we're wasting our time. So other two quotes that I loved here. I won't read them. I'll let you soak them in and sip some water. And this one, stable C++ ABI, it's useless for the platform APIs if it doesn't encompass the standard library. So you could have a compilation mode and choose between resilience and performance. And I'm going to talk a lot about this choice. Leave them a couple of seconds on screen. OK, so I titled this The King of Mixed Signals and Ambivalent Behavior. That's a weird build I have there. Anyway, I have some slide malfunction. I'll move over. So C++ does not have an ABI resilience model, so there's no official codification there. The C++ committee will just outright reject any proposal that could break ABI in existing STL components. Daniela is shaking her head, but I need proof that this is happening, that proposals that break stuff are accepted. I need proof. OK, they're not rejected, but they're not considered. Am I doing this better? OK. I'm looking constantly at Daniela to see if she shakes her head. So, but I need proof that someone got a proposal that breaks something. OK. C++ will not officially commit to guaranteeing ABI stability either. So that's interesting. So we frown upon standardizing stuff that could break clients, but at the same time, we're not committing to stability officially. And of course, this is the tricky bit where people usually point fingers at implementers and say that they're holding back on improvements, on existing standardized stuff and implementations that could be improved, but implementers choose not to do them because then they would hurt adoption or upgrades and so on. So that's another thorny issue. OK. OK, now I'm getting to what Daniela mentioned. So in the Prague discussion, the committee decided it's not in favor of breaking ABI 423. So I qualified that properly. Is in favor of an ABI break in a future version of C++, but when that will happen, we don't know. We'll take time to consider proposals requiring ABI break, as in, sure. At the same time, will not promise stability forever. So we're not committing to anything here. And of course, as always, we want to prioritize performance over stability. And I often hear some of these arguments mentioned in this topic, but I was so pleased to see them all on one slide. And this is not my slide, by the way. It is from Herb's keynote at CPPCon this year. I put the link at the bottom. So the most frequent thing I hear cited is the standard string implementation, where we did, maybe I don't need to spend time on this. Are people aware of the breaking change that happened in C++ 11? Just a few hands, unfortunately. OK, then I need to explain it very quickly. So the implementation requirement in C++ 11, when we introduced move semantic into the language, was incompatible with one of the existing implementations in standard libraries, mainly the GCC one. And that one used reference counting, and that was a breaking change. They were incompatible. So in order for that implementation to become standard compliant, they had to have an alternative string implementation that was, of course, incompatible with the other one in many ways, not just ABI. So that introduced a sort of fragmentation in the users of the library, because many of the users had to rely on the old behavior, and at the same time, others demanded the standard conformity implementation. And this was happening for over 10 years, I think, until everyone just onboarded on the new one. So these kinds of horror stories are cited usually for what can happen when you mismanage a situation like that and just throw people into a corner and force them to decide. And of course, the implementation lets you opt in either of the implementations. So you could opt in for the reference counted string or for the one with move semantics. Okay, so why do we want to break ABI? A few examples from the C++ world. Making standard regex faster, also adding UTF-8 support to it. Making hash containers faster, or having the ability to swap out the hash algorithm easily in their implementation. Better conformance, tweaks to string, vector, and other container layouts. An interesting one, if we're mentioning, we referenced calling conventions earlier, ability to pass span string view unique pointer through registers rather than memory when calling functions. This is more of a language thing rather than library thing. But again, it's a breaking change. Improving the implementation of shared pointer, improving standard mutex. Do people know that shared mutex is actually faster than standard mutex on Windows? Does that surprise you? It should. Because it's a more complicated class. Shared mutex is more complicated, but because it's newer, it uses operating system primitives that are more efficient. The old one had to support Windows XP at the time, and uses some synchronization primitives that are less efficient, because they're everywhere. And if you change that in the existing implementation, it is an ABI break, because we're changing some of these internal structures. So yeah, shared mutex is faster for now. So design choices again. Languages like C++, Rust, Carbon always prioritize faster code. They usually want heavy inlining. They want to go for CPU saturation and utilization. Mostly people in these ecosystems prefer static linking. Whereas in Swift, there's a strong tendency to prefer small code and be iCache friendly. Also fit into smaller devices. Outlining is a thing, by the way. How many people know about outlining? I know everyone knows about inlining, but outlining? One hand in the back. I won't put you on the spot. I won't ask questions, but I have a slide. And mostly dynamic linking. Yeah, they want to share libraries. So very quickly, this is an interesting one. And by the way, I linked two very nice presentations. The first one by Jessica Paquette is a shorter one, if you want to get started, but it's a slightly older version. The one at the bottom is a newer one, but it's a longer presentation that includes many other things. So you have multiple choices when opting for an optimization strategy when compiling. You can either prioritize speed or size. And on the extreme of sizing, this is the outliner, where you can actually use and this is implemented in LLVM, by the way. The compiler can actually look for similar sequences of instructions and sort of make up functions for them and move them out of line so that it reduces code bloat when it identifies similar patterns in code. It's a very interesting thing. I find it just from, I don't know, nerd point of view, I find it more interesting than inlining. Definitely more newer research domain. Anyway, aside closed. So for those who don't understand why I had Swift in the name, or why I'm mentioning Swift, or why I'm discussing Swift, is because it was the only one in the previous slide that had a yes instead of no in the bullets with all the programming languages that care about ABI stability. So Swift actually invested a lot of time in how to do library evolution and how to build an ABI resilience model. So we can have both. We can evolve things, and we can have a resilience model that works so that we don't break everyone. Don't worry, it's not all ponies and rainbows. There are some gotchas. I'm going to mention them. Swift Who, for those who want a primer. So it's a compiled language. It's not a dynamic thing. It was created to replace Objective-C, so it shares the memory model in the runtime with Objective-C, so it has some legacy. It wasn't like a brand new thing. It had to interoperate with the existing stuff. It has classes, and inheritance, interfaces, generics, every modern language facility that you might want. It uses automatic reference counting for classes. Has simple function scope, mutable borrows. You can annotate arguments nicely. Enfaces on value semantics for structs and primitive types. And only classes are considered reference types and are boxed using ARC, and they have reference semantics because they need to interoperate with the old universe of the Apple libraries and Objective-C APIs. So that was the bridge with the old world. And even collections implement value semantics using things like copy on write and ARC under the hood. So the language was designed with library evolution in mind. And I think this is essential. Principles of stable library evolution that they have is to make all promises explicit, not imply that something is stable if it's not. Delineate what can and cannot change in a stable ABI very clearly in documentation. So provide concrete commitments rather than hand-wavy stuff like we do with C++. Provide a performance model that indirects only when necessary, so you don't have, so don't pay performance costs when not needing, and I'm going to show some of these tricks. And let authors of libraries and consumers be in control by having escape hatches and opting in and out of these things. I highly recommend this talk by Doug Greger if you want to go deeper. So just a very quick example. Don't worry, I won't hit you with Swift code. That's the only Swift code I'm going to have. Maybe one more slide. So let's say we have a structure, and we might decide to reorder the ID field at the top. So we moved it up. Or we might decide to change its type from an integer to UID. Or we might decide to add an optional. By the way, the question mark isn't like pondering the universe. It means optional in Swift. Maybe adding an optional color at the end of the structure there. So the structure evolved. Obviously, it's changed size. When new fields were added, offsets of fields changed because we reordered stuff. So stuff changed. And if we're looking at the other side, someone consuming it, we have a member there of that type, and we have an array of those things. So size and stride come into play there. We're directly accessing that field, the name field there, so we care about where it's in the structure because we're directly using it. We're not calling any getter on it. So on the library side of things, type layout should be as if we had the complete view of the whole program. So the person library should lay out its type without any indirection. And the metadata required to expose layout information should be a side thing, a non-intrusive thing. And we need metadata like size, alignment, offsets of public fields. So think about having all these kinds of details on the side, like bookkeeping of describing this, this type layout. And these kinds of things can be automatically computed. And we have two strategies. I'm going to show concrete examples there of being able to have them as computed properties. Swift has the concept of computed properties. So they sort of work in a similar fashion. So they can be computed at runtime, or this step can be bypassed completely at compile time when no runtime decision needs to be made. And I'm going to explain when we can switch between those two strategies. So on the client external code, the external code indirects through layout metadata. So to access a field, it needs to read metadata for a field offset, for example, add that offset to the base object to figure out, okay, where inside the structure is my name field, and cast the pointer to load the field. If we want to deal with the stack, we have to do a similar thing. So you can actually do similar things even on the stack. Read the metadata for the size of the instance, and work with APIs such as alloc to set up the stack as needed. Where it's different is on the library side of things, the library code can eliminate all this indirection. So you don't have to go through the pseudo-computed properties or to retrieve that metadata size, because you directly have direct access to the layout of the person structure from inside the library code. So there's no need for runtime computation and to access that metadata. So, and this hash actually has some LLVM support. For example, I mentioned laying this out on the stack. LLVM has support for dynamically sized things on the stack, and Swift makes use of these. So you can have a local variable of some struct defined in a stable library, and you don't have to know its size at compile time. You can compute these things at load time. For example, if you're consuming this from a dynamic library, from a shared library, when you load that library, the loader can do all these metadata queries, and it caches all these things for performance. So it only does it once when you load the library. And it keeps a side bookkeeping table for all these computed offsets, because they don't change once you have the system running. So it's not like you're hot patching things. But you don't know them at compile time. So when you load them in, when you do a DL open, for example, these things are computed and cached at runtime. So, and LLVM has this ability to dynamically lay out these things on the stack, for example, if you want to store them on stack. So you're not confined to heap allocations. You can actually leverage the stack. So how does Swift handle this juggling between when I want to be resilient and when I want all the performance? So Swift does this using resilience domains. So these are parts of your application that are where you define some boundaries. For example, parts that are always compiled together are part of a resilience domain. For example, the person library there, so all the green stuff are separate domains. So all the stuff that is compiled together are part of a resilience domain. And inside that domain, they have intimate knowledge of their layouts, and they don't need any special handling. Whereas when you have connections, so the arrows between the resilience domains, when you cross these resilience domain boundaries, then you have to do this runtime patching where you need to compute those exact layouts using the exposed metadata. So you only pay the cost of ABI resilience of this model. You only pay the cost when you cross these boundaries. So across resilience domains, you maintain a stable ABI. So users see a stable version of each other, or at least a predictable way of interacting with each other. And within a resilience domain, all implementations details are fair game. You can change stuff. You can no indirections, no performance costs, no guarantees made. So it's as if no such system is in place. And of course, optimizations need to be aware of these boundaries. You can go all the way up. So if you, to the extreme, you don't care about, you say, okay, I don't care about this at all. You can consider everything a single resilience domain. You say, okay, I'm completely in a bubble. I don't care about the world. So you can consider everything one resilience domain. So everything is fixed at compile time, no cost, you don't pay for anything. So that's the extreme case, but that defeats the whole purpose. By default, a type that is defined in a dynamically compiled library has a resilient layout. That's the default. Size, alignment, stride of that type aren't statically known to the application. It must ask the dynamic library for its value witness table. Values witness table is sort of similar to how vtables work, or the same kind of thing. It's a side bookkeeping information that you query at runtime. So this is where you go to figure out, for every type that you deal with, to figure out its layout. Everything, all the details required by its layout. And I mentioned this is cached information. So you do these calculations, these synthetic values just once when you load that library. And then you just have the values pre-computed. But it is an indirection. But it's the kind of thing that you expect from, I don't know, vtable access. Inside the boundaries of a dynamic library, where all the implementations are statically known, the type is handled as if it's not resilient. So no indirections, no performance cost, no nothing. I mentioned that already. What I love about this is that it's a default. So you have to opt out of resilience if you don't want it. And there are some escape hatches, a few of them. For example, you can choose to explicitly inline a function, and that prevents any changes to the function semantics because it's inlined in the usage location, in the caller. So of course you cannot change its implementation because then you're going to have multiple versions of that thing. So when you opt in into this mechanism, of course for performance reasons, you give out any future flexibility. Fixed layout, it's another attribute that you can use to be explicit, to say, okay, I want to opt out of resilience for this type. I know I'm never going to change it. Famous last words, right? But in all fairness, this is called pair. What else can you do with it? But anyway, famous last words, fixed layout. So
you'll get a plus per pair if you switch members.
Yeah, possibly. Yeah, if there are different types, you could get that. Sure, that's a good argument. Yeah. So sorry, it's fixed. So this is another escape hatch for a type. Of course, I mentioned this is not all perfect. So there are some difficulties and some disadvantages, of course. You have a fairly large runtime component, although it's a statically compiled thing and it's highly performant. It's an operating system level language and runtime. It's a fairly large runtime. It's not a thin thing like the C runtime, for example, right? So you have the runtime type layout. You have those operations that need to happen when you load the library. I mentioned those. By the way, you cannot really safely close a dynamic library because bad things will happen. You have handling of the metadata at runtime. You have those witness tables and indirections that you need to deal with. Generics are particularly hard to deal with. And this is the part of the talk that I actually cut. But I'm happy to talk about these things if you want after that. So there's techniques, because dealing with generics in a resilient manner is very, very difficult. So and this is because for performance reasons, you generally want monomorphization for generics. That means have stamp out concrete types for particular generic types that you're actually using in the application. But that prevents having monomorphization commits concrete layout to those generics. And there's techniques to go the other way, like reabstraction. Anyway, I won't go into details because I prefer to have more discussion afterwards. So every language feature is harder to design. You don't get to escape this one. So sure, you have the flexibility of having resilience domains, but you have to think about when you're designing things. You cannot just blindly blast away any proposal for a change without thinking about the consequences. For example, reordering a pair for better access. There's also, because of the deployment model, because these runtimes and libraries in Swift are deployed with the operating system, you have weird limitations where you're compiling a thing and you want to use the, I don't know, fancy new language feature. But if you're targeting an older operating system version, you cannot really use it because then you'll have an older runtime and so on. So there are weird artifacts like that. So it's not perfect. I'm not claiming to be. I want to close on a sort of positive note for C++. I think there is a path forward even for C++. It's not Swift-like, but we can learn from that. lib C++ aims to preserve a stable ABI to avoid subtle bugs. Yeah, no surprise there. And at the same time, you want to make ABI breaking improvements and the user to be able to opt in. So there's ways that you can specify which ABI version you want at build time. Right now, this is what you have. 1 means, and that's the default, means stable. 2 means whatever you have there, give it to me. And 3 is for later, when 2 becomes the stable one. So, okay, it's not perfect, but it's a way forward. And if you always want to use the most cutting-edge version, there's a separate define that you can use. This is a nice article if you want to read all about these details. So I have time for questions and comments. I do accept comments as well. So that's it. I have a couple of minutes for interaction on record or afterwards, as much as you want. Go. Please, if you can, please use the microphone so that I don't have to repeat myself.
Hi, Victor. Thanks for doing this talk. I have a question just about your opinion. So,
I have only opinions, nothing else.
Perfect. So you probably know about scoped lock and how it is like a different name to lock guard because that would break API.
Exactly.
That seems a bit insane.
Same thing applies with the mutex example I gave. Yeah.
I'm not sure I agree, because logguard is a type that is specifically designed to be inside the function, right? So it's not really designed to be on the inside of a class that is provided to you by its library. So my question is, do you think there is some reasonable way to say, okay, these types we really care about ABI, and these types we don't care about ABI, and kind of that's the separation or something like that? Thank you.
I wish there was, but people don't think in such a granular fashion, at least not in C++. I haven't seen such discussions. So we sort of have this idea of break everything or break nothing. Sort of when eventually we'll decide that we're going to accept a breaking change to the implementation, and I'm not even talking about a standards stance, official stance. I'm talking about a vendor. Let's say a vendor decides to break things. They usually see this as okay, this is our opportunity. Pull in all the stuff that we've been holding back, like open the floodgates, like fix all the types, fix all the bugs, and then we'll freeze it again for 10 years. So this is the kind of thing I'm seeing, and this worries me, because this wholesale approach of, sure, we'll decide next year or the next version of whatever great implementation, we're going to do all the breaking stuff, and we're going to land all our PRs that we've been holding for 5 years, and we're going to fix everything and users be damned, and then we're going to freeze it again for 10 years. I don't believe that. What you say, a more granular opt-in approach and being more explicit on a per-type basis, it would be much more flexible, but I've yet to hear some ideas in this space. All I see is all or nothing. People are all or nothing.
So you made comparisons with Swift and Rust, for instance, which are, to my knowledge, controlled by single organizations. I would also include Java in this kind of language. And I think it's a bit unfair, because C++ is a very diverse language considering platforms, architectures, implementations. And I've heard this from people outside of the C++, so that come from Rust, for instance, that say the standard should say this and this and this and should define all these things. And I'm not convinced why is ABI not a quality of implementation issue. So provocatively, you are principal engineer for Visual C++. Why do you need the committee to tell you what to do?
I won't comment for my employer here.
Okay.
But I can comment on the whole way.
Maybe that's fine. Then let's.
Yeah. So my personal opinions don't necessarily align with the business objectives.
Then let's say it's about a different implementation, like GCC. Why does the committee need to tell the GCC people what to do? Or maybe if you don't want to answer, that's fine.
I don't think they're necessarily tied together. I think you are right. To some degree, it's an implementation quality thing. But implementations have users, and the engineers working on those implementations would want to ship you the best possible solution they have. They just have to think, they have to choose right now. They have to choose if everyone is going to be able to use the latest and greatest, or if they get to ship the brilliant V2 or the brilliant implementation. So you have usage constraints, whereas things like you mentioned, like Rust or Swift, Swift has the advantage of sort of although it's an open source project, it's sort of a single strong hand organization, right? So it has more tight control over its destiny, let's say. Also, traditionally, developers in that ecosystem are much more eager to upgrade. So they usually, and when they make changes that are difficult, they also provide extraordinary tooling to help with those migrations. They provide excellent tooling for that. And they're very aggressive about it. They will push their users. Even if it's uncomfortable, they will choose the immediate discomfort for the long-term better outcome. So Apple will push their users, and generally that ecosystem of users expect this kind of thing, where they're, okay, they might scream, they might make a fuss about it, but they know they don't have a choice. Like, they will modernize by force. So although they have like a big code base behind them, so it's a big community, they move faster. Whereas Rust has, although it's a mature ecosystem, it doesn't have as much code as Swift or C++. So it's different. I agree. It's unfair to compare. But my point wasn't to shame or compare. My point was, can we learn something from the others? Can we borrow something, right? Not everything is applicable. We cannot opt into all the fancy things we see, but just ignoring what happens over the fence doesn't solve our problems if we don't have any better solutions. So
thanks.
That's the spirit. The spirit is not like compare. The spirit was, can we learn something? And we have proof that it can be done. Sure, in a different environment, but it can be done. These are not unsolvable engineering problems.
All right, thank you.
Sorry, Victor, we're almost out of time. I'm going to allow Mark.
Last question.
Last comment.
Comment.
Yes.
Excellent.
Yeah, I work on lib C++, and yeah, we have this unstable ABI, but there are really no plans to make it stable in the near future, especially because ABI issues. But there are some people who compile everything from scratch, and they use the unstable ABI because of performance reasons. So.
Yeah. So you support my last slide, basically, right?
Yeah, but the problem I always see is that it's hard to...
No? What did I do? This one?
Yeah, but there are no concrete plans to freeze it too. So
I didn't claim that. Yeah. But if you want, at least there's a way to opt in the latest and greatest. There is a way for this implementation, not for others. So thank you. Anyway, so we have to wrap up officially, but I'll be on the hallway, so catch me for everything.